Hello, everyone. Welcome to the second lecture of AAE 301. In this lecture, we will be talking about complex numbers. So let's start with the definition of a complex number. And in order to understand the definition, let's review the imaginary unit together. So the imaginary unit is usually denoted as I, and it represents the square root of -1. And there's something else that you should know about the imaginary unit. So the square of I will be square root of -1 multiplied by square root of -1. And that's gonna be -1. And then the cube of I will be I times the square of I, which is equal to I times -1. So that's -I, and the quadrant of I is going to be the square of I times the square of I. So that's -1 multiplied by -1, which equals to 1. All right, this is what you need to know about the imaginary unit. Now let's take a look at the definition of a complex number. So a complex number, gamma, is a number that is in the form of x plus I, y. So here, x and y are real numbers. And moreover, we say the real part of the complex number gamma, which is denoted by RE gamma, will be x. And then the imaginary part of the complex number gamma will be denoted by IM gamma, and that's gonna equal to y. So for example, if we look at this complex number, gamma equals to 2 minus 3i. The real part of this complex number will be 2, and the imaginary part of this complex number will be -3. Okay, now let's see how we can do addition and multiplication on complex numbers. So first, let's look at these two complex number, gamma 1, which is equal to x1 plus I y1, and gamma 2, which is equal to x2 plus I y2. The addition of these two complex numbers can be computed as gamma 1 plus gamma 2 equals to x1 plus I y1 plus x2 plus I y2. So to sum up these two complex numbers, we simply add the real parts and the imaginary parts separately. So here we will have x1 plus x2 plus I times y1 plus y2. Great. And now let's look at how we do multiplications on these two complex numbers. So the product of gamma 1 and gamma 2 will be x1 plus I y1 times x2 plus I y2. So now we expand the product. We will get x1 x2 plus x1 I y2 plus I y1 x2 plus I squared y1 y2. So here we know that I squared is going to equal to -1. So here we're going to replace it with -1. And now we again sum up the real parts, and we will get x1, x2 minus y1, y2. And then we sum up the imaginary parts, we'll get x1, y2 plus y1, x2. So for example, if we have two complex numbers, gamma 1 equals to 2 plus 3i, and gamma 2 equals to 4 plus 2i, the summation of these two complex numbers will be 2 plus 3i plus 4 plus 2i, which equals to 6 plus 5i. And the product of these two complex numbers will be gamma 1 times gamma 2 equals to 2 plus 3i times 4 plus 2i, and that's gonna be 2 times 4 minus 3 times 2 plus I times 2 times 2 plus 3 times 4, which equals to 8 minus 6, that's 2, plus 4 plus 12, 16, 16i. All right, great. Now let's talk about how we can visualize the complex number. So to visualize the complex number, we can draw them on a complex plane. So the horizontal axis of the complex plane will be the real part of the complex number, and the vertical axis will be the imaginary part of the complex number. So for example, if we have a complex number that is equal to, say, 1 plus I, then we have 1, 1, and this point here will be gamma 1. And similarly, if we have another complex number which equals to 2 plus, say, 3i, we have 2, 3, so this is gamma 2. Okay. Now let's talk about the complex conjugate of a complex number. So if we have a complex number that is gamma equals to x plus iy, the complex conjugate of gamma is denoted by gamma bar, can be computed by reversing the sign of the imaginary part of gamma. So that's basically going to be x minus iy. So here, this is the complex conjugate of gamma. And notice that here, what we did is we reverse the sign of the imaginary part of gamma. Okay, so now with this new definition for basically the complex conjugate of a complex number, we can come up with a way to compute the real part of the complex number and the imaginary part of a complex number. So now the real part of the complex number gamma can be computed by this expression here. Essentially, this is gamma plus its complex conjugate divided by 2, and then the imaginary part of the complex number gamma can be computed by looking at the difference between gamma and its complex conjugate divided by 2i. So now let's see why these two expressions works. So let's take a look at the first one. Let's take a look at the how we can compute the real part of the complex number. So here we have gamma plus the complex conjugate of gamma divided by 2. So now to see why this works, now let's substitute gamma equals to x plus iy, and gamma, the complex conjugate of gamma, equals to x minus iy into this expression. So here we will have x plus iy plus x minus iy divided by 2. And now if you look carefully at the numerator part of this expression, you will see that the imaginary parts will cancel out each other, and we will be left with the real part times the 2 times of the real part of gamma. So now if we divide this by 2, what we will be left with will be x, which is the real part of gamma. And now we can do, now let's see why this expression for the imaginary part of gamma works. So again, we substitute gamma equals to x plus iy and gamma bar equals to x minus iy into this expression, and we will get x plus iy minus x minus iy divided by 2i. So if you look at the numerator part, you see that the real parts cancel out, and we're left with 2i times y. And now we divide this by 2i, and we will end up having y, which is the imaginary part of the complex number gamma. Okay. All right. Now it's time for another example. Let's see if we can compute the real part and imaginary part of this complex number. So we have 2 plus 3i in the numerator and 1 plus 2i in the denominator. So to compute, to evaluate this, to compute the real part and imaginary part of this complex number, we need to do something called the real, what was that called? Rationalization. Yes, rationalization. So in order to do that, we will multiply we will multiply 2 plus 3i and 1 plus 2i by the complex conjugate of 1 plus 2i at the same time on the numerator and the denominator. So here we will have 1 minus 2i and 1 minus 2i. And here what we'll end up with is 1 plus 2i times 1 minus 2i and 2 plus 3i times 1 minus 2i. So this is going to be 1 squared plus negative 2 squared, and the upper part will be 2 plus 6 plus I times 3 minus, oops. So in the end, we will have 8 minus I over 5. So the real part of gamma is 8 over 5, and the imaginary part of gamma is negative 1. All right. And now let's take a look at another way to express the complex number. So just now we have seen one way to express the complex number, which is gamma equals to x plus iy. So this is what we call the Cartesian form. And now let's let's see how we can express the complex number in polar form. So now I'd like to draw your attention back to the complex plane that we have just seen. So this is the complex plane. And this is X, and this is Y. And here's gamma. So in order to express the complex number gamma in the polar form, there are two things that we need. One is a directional vector, and the other is the length of that vector. So essentially, what I'm saying is we we can create a vector. We can create a vector that points to this complex number on the complex plane from the origin. And now this vector can be expressed as its length multiplied by like a unit vector, unit directional vector. So the length of this vector can be the length of this vector is going to be called the magnitude of the complex number. And it's usually denoted by the absolute value of gamma, and it can be computed by looking at the square root of the sum of the square of the real parts and the imaginary part. And the other thing that we need is the unit directional vector. So for the unit direction vector, we will need to rely on the Euler formula. So according to Euler's formula, it says that e to the power of I theta is equal to cosine theta plus I sine theta. So let's now draw this on the complex point. Here we have the complex plane, and if this is theta, then cosine theta will be this cosine theta, and this will be sine theta. So essentially, e to the I theta will be a complex number that points to the direction from the origin to this complex number gamma. And now let's see why this is a unit vector, basically saying that the magnitude of this complex number is equal to 1. So let's look at the magnitude of this complex number. We have e to the I theta equals to cosine theta plus I sine theta. And then according to, and so this is the real part. This is the real part, and this is the imaginary. So just now we have said that the magnitude of a complex number can be computed as the square root of the sum of the square of the real parts and the imaginary parts. So here we will have the square root of cosine theta plus the square root of sine theta. Oops. And we all know that this summation will equal to 1. So here we will have square root of 1. And square root of 1 is basically just 1. So that's so now we see that the magnitude of e to the I theta is 1. And this basically says that this will be a unit vector. And and um, and here's some other things that you may need to know about e to the I theta. The first thing is the complex conjugate of e to the I theta is cosine theta, the complex conjugate of cosine theta plus I sine theta. And this will equal to cosine theta minus I sine theta. And if we look at e to the negative I theta, we will get cosine negative theta plus I sine theta, oh sorry, I sine negative theta. So here we will have cosine theta minus I sine theta. And this tells us that the complex conjugate of e to the I theta will be e to the negative I theta. And with this, we can now see why cosine theta equals to uh, e I theta plus e negative I theta divided by 2, because this is basically going to be e I theta plus the complex conjugate of itself divided by 2. And um, we know that the real part of a complex number can be computed by uh, uh, adding itself with its conjugate and divided by 2. So, and also we know that e to the I theta equals to cosine theta plus I sine theta. So here we are actually just evaluating the real part of e to the I theta, and that gives us cosine theta. Oops. And similarly, for sine theta, you see that it's equal to e to the I theta minus e to the negative I theta divided by 2I. And again, we can replace e to the negative I theta by the complex conjugate of e to the I theta. Here we'll have I theta conjugate divided by 2I. So here what we're evaluating is just basically the imaginary part of e to the I theta. That's essentially just sine theta. All right. Okay. Now back to the polar form of a complex number. So here now let's see how we can express the complex number gamma in polar form. So again, gamma equals to x plus iy, and this is what it looks on the complex plane. Oops. 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 This is what it looks like on the complex plane. So now we can express it as the magnitude times the unit directional vector. And here the angle theta is going to be the arctangent of y over x. Okay, so this is the polar form. I'm gonna write it, polar form, and this is Cartesian. Great. So let's take a look at some examples. Say now we have a complex number that is gamma equals to 1 plus I, and we see that this is in Cartesian form. And now let's see how we can express this in polar form. So the first thing we need to do is to evaluate the magnitude of this complex number. So that's going to be square root of 1 squared plus 1 squared, and that's square root of 2. And then the angle will be the arctangent of 1 over 1 in this case. So that's basically just 45 degrees or pi over 4. It may make more sense if we draw it out. So here we have this complex plane in, and 1, 1 is right here. This is gamma. This is 1. This is 1. So you can see that the angle here is 45 degrees. Okay, now that we have determined the magnitude and the angle of the complex number on the complex plane, we can now express this complex number in polar form as gamma times e to the I theta, which is gamma square root of 2 times e to the I pi over 4. Okay. You may wonder, why do we need to know about why do we need this this other representation for a complex number? So it turns out that the polar form or the polar decomposition of a complex number can be useful in computing roots and powers of the complex numbers. So say now we have this complex number gamma, which is equal to x plus iy, and we want to compute the nth power of gamma. If you do it without converting gamma into polar form, then this will be very tedious because you will have to multiply x plus iy for n times. But then now if you express gamma in polar form, we will have gamma times e to the I theta to the power of n. And now this will equal to the nth power of the magnitude of gamma times e to the I n theta. So now we can apply the Euler formula to convert this expression back into the Cartesian form. So we will have gamma, the magnitude of gamma to the power of n times cosine n theta plus I sine n theta. And this will end up being to the power n cosine n theta plus I gamma to the power n sine n theta, which is much easier, right? And similarly, if you want to compute the roots of the complex number gamma, say 1 over n, gamma to the power of 1 over n, the nth roots, then we can do this simply by this. So we write gamma as gamma times e to the I theta to the power of 1 over n. And here we can expand this, and we will get e to the I theta over n, right? And now we can convert this back to the Cartesian form by applying the Euler's formula. So we will get times cosine, theta over n plus I sine theta over n. And we will end up having times cosine theta over n plus I gamma 1 over n sine theta over n. Okay. Again, now it's time for another example. So let's look at this complex number gamma equals to 1 plus I. And just now, let's see how we can compute the cube of gamma. So here we have gamma cube. And first, so just now we have already found the polar form of this gamma. So we know that 1 plus I equals to square root of 2 times e to the I times pi over 4. So gamma cube will just basically be square root of 2. Oops. This is going to be 1 plus I cube, and this is equal to square root of 2 times e to the I pi over 4 to the power of 3. So here we will have square root of 2 to the power of 3 times e to the I 3 times pi over 4. So this is 2 square root of 2 times e to the I times 3 over 4 pi. So now we can convert this back into the Cartesian form by applying the Euler's formula. So we will get 2 square root of 2 times cosine 3 over 4 pi plus I. And that's 2 square root of 2 times cosine 3 over 4 pi plus I 2 square root of 2 sine 3 over 4 pi. And that will end up being negative 2 plus 2i. All right. And another advantage of expressing the complex number in polar form is that it will be easier for us to compute this problem. So we have this messy expression here, gamma 1 and gamma 2 over gamma 3, gamma 4, gamma 5. So to evaluate this this fraction, originally what we'll have to do is we will have to first compute what's gamma 1 times gamma 2. So we will have to have gamma prime equals to gamma 1 times gamma 2, and this will equal to some x prime plus I y prime, and then we will have to evaluate this gamma double prime, which equals to gamma 3, gamma 4, gamma 5, and this will be some x double prime plus I y double. And then gamma can be computed as gamma prime over gamma double prime, and this equals to x prime plus I y prime over x double prime plus I y double. And again, we will have to do the I forgot the terminology again. Basically, you will have to rationalize it. Yes, you have to rationalize this by multiplying the the complex conjugate of gamma double prime in the denominator and the numerator at the same time. And you can see how tedious this can be. But with the polar form, we can now evaluate this fraction by doing something like this. So we can rewrite gamma as the magnitude of gamma 1 times e to the I theta 1 and times the magnitude of gamma 2, times e to the I theta 2 over gamma 3 e to the I theta 3 times gamma 4 e to the I theta 4, and then gamma 5 e to the I theta 5. And so we can collect the real, um, we can now further express this as gamma 1 times gamma 2 over gamma 3, gamma 4, gamma 5 times e to the I theta 1 plus theta 2 minus theta 3 minus theta 4 minus theta 5, which is much simpler, right? So now let's take a look at another example. So let's see how we can evaluate this complex number. We have gamma equals to negative 2 plus 3i times 4 minus 2i over 1 minus 2i times 3 plus 2i. So here we have um, uh, so let's rewrite this again as negative 1 times 2 plus 3i times 4 minus 2i, and then 1 minus 2i and 3 plus 2i. So in total, there are 5 complex numbers. So the magnitude, so they are, I'm gonna write like this. So this is gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. So we can rewrite this as gamma 1 times gamma 2 times gamma 3 over gamma 4, gamma 5, and times e to the I theta 1 plus theta 2 plus theta 3 minus theta 4 minus theta. So for this part, for the magnitude part, let's see what it will be. So the magnitude of gamma 1 is 1. The magnitude of gamma 2 is square root of 2 squared plus 3 squared. And the magnitude of gamma 3 is the square root of 4 squared plus negative 2 squared. Now we divide it by the magnitude of gamma 4, which is 1 squared plus negative 2 squared, times the magnitude of gamma 5, which is 3 squared, square root of 3 squared plus 2 squared. And so here we see that we can cancel out these two terms because they're identical and non-zero. And here we will be left with this is take a look. Did I do something wrong here? 2 plus 3, 1, 2, 4, 2. Okay, maybe not. Okay, so this will equal to 16 plus 4 square root of 16 plus 4. That's 2 over 5. 2 square root of 5. This is square root of 5. So we will have this whole thing equal to 2. And then now let's see the angle of each complex numbers. This will be e to the I. The angle of theta 1 will be pi. The angle of theta 2 will be arctangent of 3/2 plus arctangent of -2/4 minus arctangent of -2/1 minus arctangent of 2/3. And this is roughly going to be -2. All right. And on this page, you see there's a proof for the Euler's formula, and you can take a look at it if you are interested. Basically, you can obtain this result by looking at the Taylor expansions of these three functions, exponential to the power of x, and cosine theta and sine theta. And then you essentially just substitute x with I theta, and then you can rearrange the terms. Basically, you sum up all the real parts and sum up and the imaginary parts separately, and then you will see in the end you will get cosine theta for the real part and sine theta for the imaginary part. Another another usage of the polar form is that it allows us to compute the root of this polynomial. So lambda to the power of n minus gamma equals to 0. So according to the fundamental theorem of polynomials, we know that the number of roots will equal to the highest power of the polynomial. So in this case, we have lambda to the power of n. So that means that we will have in total n we will have n roots. This is according to the fundamental theorem. Fundamental theorem of polynomials. Okay. And now let's see how we can find these roots. So here we have lambda n minus gamma, which is a complex number. Equals to 0. So again, we can let's move gamma to the right hand side, and we can now, and let's express this gamma in the polar form as this. Then we see that lambda is essentially just this rth roots of this whole thing. Sorry, the nth root of this whole thing. So it will be gamma to the power of 1/n times e to the I theta over n. And this is the n, and you will also see that e to the I theta over n plus 2 k pi, sorry, will also be a solution to this will also be a solution to this polynomial, because e to the I k I equals to 1 for any integers k, for any integer k. And to see this, sorry, this should be 2k I 2k pi. Yeah, to see this, we basically again have to rely on the Euler's formula. So cosine this will equal to cosine 2k pi plus I sine 2k pi. And we know that cosine 2k pi will essentially just be 1, and sine 2k pi will just be 0. So we will end up having 1. And so that basically means that if we let, uh, so that basically means that gamma to the power of 1 over n times e to the I theta over n plus 2k pi for k equals to 0, 1, 2, all the way to n minus 1 will all be a root to this polynomial equation. So polynomial equation is minus gamma equals to 0. So these basically are all the roots to this polynomial. Now let's take a look at an example. So say we have gamma equals to 1 minus I, and now we are asked to find uh, the solution to this polynomial equation. So we have lambda to the power of 5 minus gamma equals to 0. So the first thing we do again is we move gamma to the right hand side, and we have lambda to the power of 5 equals to gamma. And now we can rewrite gamma in polar form. So we have again, the magnitude of gamma will be 1 squared, square root of 1 squared plus negative 1 squared, which is square root of 2, and the angle will be arctangent of negative 1 over 1, so that's negative pi over 4. So here we have gamma times e to the I theta, and so that basically says gamma, which is equal to lambda, which is equal to gamma to the power of 1 over 5, will be this whole thing to the power of 1. So here we have uh, square root of 2 to the power of 1 over 5 times e to the I theta over 5. And this is just one root to this polynomial equation. So to find all the other roots, we will have to multiply e to the I times 2 pi k. Oh, sorry, 2k pi to this expression. Let me write this way. Square root of 2, 1 over 5 times e to the I theta over 5 times e to the I 2k pi. So just as a reminder, this whole thing goes to 1. So it does not change the result. But now with this new expression, we can find all the roots to this polynomial equation. So all the roots will be can be found by letting k to be 0 or 1 or 2 or 3 or 4. So in the end, we get lambda equals to gamma to the power of 1/5 equals to square root of 2 to the power of 1/5 times e to the I theta over 5. This is when k equals to 0. And here we will have just copy and paste this. C 4 5. So now, so when here, let's see, this is k equals to 1. uh, Wait a second. Oh, I'm so sorry. I'm so sorry. Um, Let me talk about this again. So sorry, I made a mistake here. Let me talk about this again. So here, let's go back to this page. So let's see how we can use polar form to obtain uh, the solution to this polynomial equation. So we have n to the power of n minus gamma equals to 0. So gamma here is a complex number. And we know that according to the fundamental theorem of polynomials, we know that there are going to be n roots. And this is according to fundamental theorem of polynomials. Okay, and the roots, so the root is going to be gamma to the power of 1 over. Okay, so let's see how we can evaluate this using the polar form. So first thing is we move the gamma to the right hand side, and then we express this using the polar form. So here we have it. And then the other thing is let's we can multiply e to the this whole thing by e to the I k 2k pi. And the k here, k is integers, is an integer. And this will not change the result because e to the I k pi, e to the I to k pi will always equal to 1. And to see this, let's apply the Euler's formula. So we know that e to the I to k pi will equal to cosine 2k pi plus I sine 2k pi. And cosine 2k pi essentially is 1, and sine 2k pi essentially is 0 when k is an integer. So that's why we will end up having 1. So then so now we will have lambda to the power of n equals to the magnitude of gamma times e to the I theta plus 2k. And here k is n. And now we can evaluate lambda simply by taking the nth root of this whole thing on the right hand side. So we have this. The nth root of this thing, k is an integer. So in the end, we will get something times e I theta plus 2k pi over n. And so now to obtain all the roots for this polynomial equation, we can simply let k to be from 0, 1, 2, all the way to n plus 1. And this will be the nth roots for this polynomial. And now let's take a look at an example. Say gamma equals to minus I. And now we are asked to find the fifth roots of gamma. So the fifth root of gamma will basically be the solution to this polynomial equation. Lambda to the power of 5 minus gamma equals to 0. So this is solution. And now let's see what lambda is. So we have lambda to the power of 5 equals to gamma. And now let's rewrite gamma in the polar form. And to do that, we need to evaluate the magnitude and angle of gamma. So the magnitude is going to be 1 squared plus negative 1 squared. The square root of 1 squared plus negative 1 squared, which is square root of 2. And the angle will be the arctangent of negative 1 over 1. And that's negative pi over 4. So here we have this theta. And now we multiply this by e to the I 2k pi, and k is integer. And we get gamma ei theta plus 2k pi, k is integer. Then this implies that lambda is essentially just gamma to the power of 1 over 5 times e to the power of I theta plus 2k pi over 5. So that's square root of 2 to the power of 1 over 5 times e I negative pi over 4 plus 2k pi over 5. And here k will be from 0, 1, 2, 3, 4. So we have all the roots now, and they are lambda 1 equals to square root of 2 of 5 times e I negative 20 pi plus oh, sorry, just this. This is when k equals to 0, and then we have square root of 2. The second root is square root of 2 to the power of 1 over 5 times e I negative 1 over 20 pi plus 2 over 5 pi. And this is when k equals to 1. And similarly, we can do the same all the way to the fifth roots, which is going to be 2 to the power of 1 over 5 times e to the power of I negative 1 over 20 pi plus 8 over 5 pi. And this is k equals to 4. Okay. Now we have it. And so now it should be it should make sense to you for how you can compute uh, the all the roots of this polynomial. Lambda to the power of n minus 1 equals to 0. Basically, you can just follow the same procedure to find all the n roots of this polynomial. And in the end, you will see that lambda will equal to e to the power of I 2k pi over n. And k is going to be from 0, 1, 2, all the way to n. And here's an example for n equals to 75. And all the dots here on the complex planes are the roots to this polynomial. And if you can try to count it, and you will see in the end, there will be 75 roots in total. And the last thing I want to talk about before I end the class today is how we can use the Euler's formula to prove some trigonometric identities. So let's see this identity here, cosine theta times cosine phi equals to cosine theta plus phi plus cosine theta minus phi over 2. So let's see how we can prove this using Euler's formula. So we have cosine theta equals to e to the I theta plus e to the negative I theta over 2, and cosine phi equals to e to the I phi plus e to the negative I phi over 2. And now we substitute these two expressions into this equation here. Sorry, this expression here. And we will get e to the I theta plus e to the negative I theta times e to the I phi plus negative, plus e to the negative I phi. And now we expand this, we will get 1 over 4 and e to the I theta plus b plus ei theta minus b plus e I b minus theta plus e negative I theta plus phi. And we can collect them again. We can rearrange them, and in the end, we will see that this will be 1 over 4 times e I theta plus e negative I theta plus b plus e I theta minus b plus e negative I theta minus b. So you will notice that this is the complex conjugate of, so if this is gamma, then this is gamma bar, which is the complex conjugate of gamma. And this term here, if this is gamma prime, then this is the complex conjugate of gamma. So here we will have, we can rewrite this as 1 over 2 times 1 over 2, 1 over 2 times gamma plus the complex conjugate of gamma divided by 2 plus gamma prime plus the complex conjugate of gamma prime divided by 2. And here this will be 1 over 2 times So this thing here will essentially just be the real part of gamma, and this thing here will be the real part of gamma prime. So we will end up having cosine theta plus v and cosine theta minus v times 1/2. And this is exactly what we're looking for. Okay, and you can also, and here I'm going to leave this page for you to practice, but essentially the idea is the same. Basically, you can just express cosine and sine using the Euler, using the exponential to the I theta, which is basically by applying the Euler's formula, and then you can expand the product, and after reorganizing every term, you will get this expression here. And this is the end of today's lecture. Thank you.